Okay, in this review video, we're going to look at our pre-calculus final exam review for the second semester. This is Mrs. Finnegan. We're going to look at several of the problems from the beginning of your review. So looking at problems 1 through 5, you can see I've identified what the parent function is that would create a graph, the parent function being the simplest form of the function that you could get. So the ones that I do want to make a comment on are number 4 and 5, logarithmic. You can tell the difference between a logarithmic because if it goes down, it approaches an asymptote, means it's going to keep going, whereas a square has a definite starting point and it doesn't continue to go down. So just make sure that when you're looking at something that looks square root or logarithmic and you're not really sure which one it is, that you look to see if the graph would continue or if it has a definite starting point. That is kind of the big thing to look for. So now we're going to look at some function recognition. Problems 6 through 11, we're matching the graphs on the left-hand side with the equations on the right. And I've put up here some basic polynomial characteristics that you want to look for and identify from your equation. Okay, so first, and probably the most important, is to identify the basic shape. And you can discover the basic shape by looking at both degree and the sign of the lead term. So our lead term is the highest exponent term, and it includes both the variable with its exponent and any coefficient that goes in front of it. So odd degreed functions, odd degreed terms, are going to have signs going in opposite directions, and even degreed functions are going to have ends that go in the same direction. Also, we care about the sign of it. If it's a positive term, like number 8, then generally the graph is going to be increasing. So that means from left to right, we're going to see it going from the bottom to the top. Whereas if we have a negative odd degree, we're going to go from the top to the bottom. Think of a linear equation if you're not really sure, because linear is an odd exponent. So positive linears increase from left to right, and negative linears decrease from left to right. So that same holds true for any odd function. Okay, so our even functions, okay, so let's go ahead and take care of number 9 is going to be a positive odd, so it's going to increase going from left to right. And number 11 is a negative odd function, so it's going to decrease going from left to right. Now notice I'm just drawing the arrows of what the ends of my graph are going to look like, not necessarily paying attention to what the middle of the graphs are going to be yet. If we look at 7 and 10, those are our even functions, even degreed functions. So those are going to be more like a quadratic, where both ends point in the same direction. This one's easy. Positive points up, negative points down. And again, I'm just talking about the ends of the graph. And so based on that, we can narrow down a large majority of which equations are going to match. The next thing that we want to look at in order to be able to determine which of these graphs are going to match the equations is we want to look at the number of possible routes, turning points. Turning points are typically the maximum you can have is going to be one less than your degree. So if I have a degree of 5, then at most I'm going to have 4 turning points. It doesn't mean I will have 4 turning points, but I could have up to. So if I have a degree of 4, I could have up to 3 turning points. Okay, so let's list out our turning points. Now I can, once I have this basic information identified for each equation, I can go over here to my graphs and start matching. So I look at A and I can see that it's an increasing graph. It starts low, finishes high, and it has 2 turning points. So that means it's probably a positive cubed equation, which I see the only one I have is number 9. So number 9 is A. The next one, both ends point up, and I have 1, 2, 3 turning points. That means I have a 4th power polynomial. So that's number 10. Okay, on C, both ends point down, so that means I have an even degree, and then I have 1, 2, 3 turning points, so that must be number 7. Okay, on D, I'm going from top to bottom as I go left to right, so that means it's a decreasing function, that's negative, and I have 2 turning points, that means I'm probably cubed, so that's going to be number 11. And so these bottom 2, I can see they both have 1, 2, 3, 4 turning points. 1, 2, 3, 4. And the ends are pointing in the opposite direction. These are my to the 5th powers. So notice E goes from top to bottom. That's a decreasing function, so that means it's my negative graph. So that's 6. And F goes from bottom to top. It's an increasing graph. So that's my equation number for number 8, or my graph for equation number 8. So there you have it, the answers for 6 through 11. So let's go ahead and turn the page and let's look at function recognition for rational functions. All right, so when we're looking at, we're going to look at problems 12 through 15, and I've typed up here several rational characteristics. Oops, before I continue on here, one thing I do want to point, I did have two other factors that you could consider. If for some reason the basic shape and the number of turning points did not narrow down your selections, you could always look at the y-intercept, which is going to be your constant value on an equation. If you don't see a constant at 0, that means you cross at the origin. So like E, we can see crossed at the origin right here. Or, for instance, on graph C, 4 crossed at y equals 4. Also, if y-intercepts, you could also then go to your factors, see where you cross the x-axis. You could factor each equation, but I would save that step only if you could not get all the other information on from the other characteristics. Okay, so let's now look at problems 12 through 15. Okay, so these are rationals because I have a fraction with x in both the numerator and the denominator. I am in factored form, so there's a lot of benefits to factored form, and I want to match the graphs. So whenever we're doing rational characteristics, we're going to look at 5 different things. I use the acronym RATEY, R-A-T-E-Y. R stands for roots, and we find that by setting every factor in the numerator equal to 0. A is for asymptotes. These are our vertical asymptotes, and that's where we get those when we set the denominator equal to 0. T, or t squared, stands for either tangency or togetherness, and that happens if I ever have a factor squared. If you don't have a factor square, there is no t. Okay, E stands for end behavior. What are we doing as x goes to infinity or negative infinity? Okay, and what we do to find this is it's going to be the ratio of our lead coefficients. So you find your highest terms, and you set a ratio, and we'll simplify it, and you'll see that in a second. And then our Y stands for our y-intercept. Sorry, I had a little typo there. So we find our y-intercept simply by setting x equal to 0. It's typically our constant values multiplied together. All right, so let's go ahead and look at number 12. Notice all of these look very, very similar. We're using x minus 1, x plus 1, x minus 2, and x plus 2. It's just a matter of how many of each we have in each problem. So looking at number 1, our roots, remember, are when our numerator is equal to each factor in the numerator equals 0. So that's going to happen. Remember when I say x minus 1 equals 0, when I solve for x, I get the opposite sign of how it appears in the factor. Sorry, my writing's a little scratchy. So that's going to be x minus 1 gives me a root of x as positive 1, and x plus 1 gives me a root at x equals negative 1. Okay, so I could look here and I could see my answer is either going to be B, C, or D. A doesn't fit the bill because it doesn't cross at positive 1. All right, next we're going to look at our asymptotes. That's when our denominator equals 0. So I have 2 asymptotes here. X minus 2 is going to give me an asymptote when x equals a positive 2. And x plus 2 is going to give me an asymptote when x equals negative 2. All right, so that's basically these vertical lines we could draw in our graph. Okay, we already know it's not A, but we could see that we have the same asymptote here on B. We have the same asymptote on C, and we also have the same asymptote on D. So that didn't narrow anything down other than to say that they all probably have the same asymptotes. All right, T stands for togetherness, and it only happens when you have a factor squared. So if I look in the numerator or the denominator, nothing is squared, so I don't have either. Okay, and I'll talk about what that looks like when we get it. All right, E stands for end behavior. It's the ratio of the lead coefficients. So my lead coefficients are going to be all of my x terms multiplied together along with any coefficients they might have. So on the top, I'm going to have y equals x. I'm just going to say y equals because it's a horizontal asymptote. X squared over x squared, they're the same. So the ratio then simplifies to just 1. So that means I have a horizontal asymptote when y equals 1. So I can see A, I do have that asymptote at 1. B, okay, has an asymptote at 1. C, it appears that my asymptote is at 0. And notice on C that this middle section crosses over the asymptote. That's okay to cross over the horizontal asymptote in the middle. And D appears to have a horizontal asymptote at 2. So based on that, I could probably with confidence say that my answer is B. Let's figure out the y-intercept though. The y-intercept is when x is 0. So if I put in a 0 for all my x's, I get -1 times 1 on top, so that's going to give me a -1 in the numerator. Then if I put in zeros, I have -2 times +2, that's going to give me a -4. So if I simplify it, I get 1/4. So if I go to B, it does appear that I'm crossing the x-axis slightly above, which is 1/4. So that tells me my answer to number 12 is B. Okay, so 13, I have the same x-intercepts, the roots. I have the same asymptotes. But what's different on 13 is I notice that one of my asymptotes is squared. If you have a square in the denominator, that means togetherness is with your where you have a square in the denominator. That means my asymptotes come together at whatever factor is squared. So I have togetherness at x equals -2. So if I come over here to my asymptotes, I can see that at A, my asymptote at -2, my asymptotes are going in opposite direction. That is not together. B, they're going in opposite directions. C, they are together. And then at D, they're going in opposite directions. So that means that C has to be my correct answer. I could continue my end behavior. It's still going to be x squared over x squared, which will still be y equals 1. And my y-intercept this time, though, is going to be -1 over -8. Because notice the 2 is being squared, so that's 1 over 8. Okay, on problem 14, you can see we only have one root. This time it's going to happen only at x equals -1, and it's squared. So I'm going to jump straight to the t. When you have a square in the numerator, that means you have tangency. That's saying you have a double root. If you remember back to when we talked about quadratics or polynomials, if you had a double root or a double zero, then you basically had a tangent, a turning point at that root. So here I can see the only answer that I do that, I have a single root and it turns at that -1 is going to be A, so that's going to be my answer here. Just to look at the end behavior, I still have x squared over x squared because this x is being squared, and then I have x times x on the bottom, so that's x squared as well. So that's the same. So let's see, I have tangency at x equals -1. My end behavior is going to be still y equals 1, but my y-asymptote this time is going to be 1 over -4, which is -1/4. You'll notice that on A, I'm crossing a little bit below the x-axis. And the last one, 15, we know is going to be D, but let's look at it. So if we find our roots, we can see x minus 1 is still going to give me a root at 1. X plus 1 is going to give me a root at -1. That's still the same, and I can see that happens on D. That's where I'm crossing the x-axis. I still have asymptotes at -2 and +2. Okay, so that's still good. I don't have any squares, so there is no tangency or togetherness. But what does change is my end behavior. You'll notice in my numerator, I still have x times x, so that still gives me an x squared on top, but there's this 2 hanging out, and that has to multiply with that term. It's kind of like a lead coefficient. And I still have x squared on the bottom, so if I simplify that ratio, I get y, the x squares cancel out, I get y equals 2. So that's why on D, my asymptote, my end behavior is higher than it was on the previous ones. And on this one, that 2 is going to affect the y-intercept. I get a -2 over -4, so my y-intercept this time is going to be at +1/2. So that's going to be D. So it's a very ugly D. So make sure that you understand polynomial characteristics and rational characteristics so that you could be able to match a graph with its equation without using a calculator.